Hello, and welcome to Backer Breaks It Down. In this episode, we are going to explore rational functions and their end behavior. First off, a rational function is a quotient of two polynomials. So if you look over here, x squared minus 6 over 7x is an example of a rational function. Now, end behavior. We're talking about the behavior at the ends of the graph of the function. Take a look here. Rational functions, they come in all shapes and sizes. Yeah, I see a lot of asymptotes too. Vertical asymptotes, horizontal asymptotes, something called a slant asymptote. Okay. But this episode focuses on the behavior at the ends of the function. And even those behaviors are different too. So I already had you investigate 3 different types of behavior. Let me get rid of that, okay? First of all, there was this behavior. It says rational functions whose numerators and denominators have equal degrees. And what we discovered is that when the numerator and the denominator are of equal degree, the end behavior is equal to the ratio of the leading terms. Okay, so the function f of x, the ratio of its leading terms is 5. And notice that the end behavior is also 5. G of x, its ratio is 1/2. And notice the end behavior is also 1/2. So that's one scenario. The second scenario involves rational functions where the degree of the numerator is less than the degree of the denominator, like this function right here. Notice that in the numerator we have degree 1, and in the denominator we have degree 2. Now let's take a look at the right and left ends of our function. On the right, these values are getting closer and closer to 0. We can say the same thing about the values on the left. Therefore, when the degree of the numerator is less than the degree of the denominator, our end behavior is going to be 0. And finally, there's case number 3, where the degree of the numerator is greater than the degree of the denominator. Check this out. So g of x, the numerator, its leading term is x squared. The denominator has a leading term of x. So like we've got in the numerator degree 2 and in the denominator degree 1. So the numerator is bigger. Check out this end behavior. On the left, these values are getting closer and closer to negative infinity. And on the right, the values are getting closer and closer to positive infinity. So it's an infinite end behavior. But is that how it's going to be each and every time we face this scenario? Negative infinity on the left and positive infinity on the right? Like, how do we know? I'm glad you asked. Okay. So before I talk about scenario number 3 some more, let me just remind you of our other 2 scenarios. So we have scenario 1 where the degree of the numerator is equal to the degree of the denominator. If this is true, then the limit or the end behaviors, both ends, is equal to the ratio of the leading terms. So check this out. F of x has a leading term of 2x squared on top, a leading term of x squared on the bottom. So the degrees are equal. And the ratio of those 2 terms is 2. And notice that's what the end behavior is. It's 2 on the right and it's 2 on the left. Okay, case number 2. In case number 2, the degree of the numerator is less than the degree of the denominator. So if this is the scenario, the limit or the end behavior is going to be 0 no matter what. So here on top, we have 3x. On the bottom, we have x squared. So the numerator is less than the denominator degree-wise. And check out this graph. Notice it's going to 0, closer and closer to 0 on the left, and closer to 0 on the right. Okay, so that brings us to case number 3. where the numerator is greater than the denominator. We want to know, okay, so it's infinite, but how do I know like exactly what it is? So we're going to use our good old leading term test to help us figure this out, okay? So when we were studying polynomial functions, we looked at the leading term of the polynomial, and that helped us determine what our end behavior was. So we can do the same thing with rational functions. We can look at the leading term in the numerator and the leading term in the denominator, okay? So notice numerator is greater than the denominator, okay? And we can take those two terms and we can make a ratio. And then we can simplify that ratio. So when I simplified 6x to the fourth over 2x squared, I got 3x squared. And 3x squared I can describe as being even and positive. So it's even degree, and it's a positive leading coefficient. So according to the leading term test, the end behavior on the left is positive infinity, and the end behavior on the right is positive infinity as well. So going back to our investigation in this problem here, we had x squared was the leading term on top, x was the leading term on the bottom. I simplify this and I get simply x. So this is an odd degree because it's technically 1, and it's positive. And we know that all odd positives have an end behavior of negative infinity on the left and positive infinity on the right. So that explains our case 3 summary. Okay, we still need to like compare the ratio of the leading terms, so numerator and denominator, then simplify that, use the leading term test. So let's check out some examples, okay? So in examples 1 through 6, we want to find the indicated limit. So notice that they're not asking us to find both the left hand and right hand behavior. They're just asking us to find one of those. So that's something to pay attention to, especially in case 3, because in case 3 is where the left and the right end behavior will be different, okay? So compare the degrees of the numerator and the denominator. Use our summary table here to find the end behavior. So right now it'd be great for you to pause the video, try these out, and then check back in with me. All right, so let's see how you did on these. So for all of these, what I need to do is I need to identify the leading term. So I'm just going to get out my highlighter and do that. In fact, I might just do that for all of them, okay? So like here, I've got positive 5x on top, 6x on the bottom. In problem 2, I'll have to do some calculating to figure out what's on top, okay? Same with number 3, because it's in factored form on top. But on the bottom, I have negative 6x to the fourth. So you definitely want to include the signs when you're identifying your leading terms. So like in number 4, the leading term on top is negative 4x squared, okay? So I'm just right now highlighting the leading terms on top and on the bottom, because then it's going to make it go really fast when I go and find like what the end behavior is. So going back to number 1, I see that on top I have degree 1 and on the bottom I have degree 1. So the degree of the numerator is actually equal to the degree of the denominator because both are 1s. So that means my end behavior is equal to the ratio of the leading terms. So we're talking like 5 over 6. In problem number 2, I needed to like figure out what's the leading term on top. So if I actually multiply these together, that gives me x cubed. So I have an x cubed leading term on top and a 5x cubed leading term on the bottom. So once again, the degree of the numerator equals the degree of the denominator. So once again, my limit is equal to the ratio of my leading terms. So we're talking 1/5 here. In problem number 3, I need to multiply all those leading terms together on top. And when I do that, I get 3x cubed. And on the bottom, I have negative 6x to the 4th. And then I compare my degrees. So in this problem, since I have a degree 3 on top and a degree 4 on the bottom, the degree of the numerator is less than the degree of the denominator, which means my end behavior is 0. In problem number 4, on top I have negative 4x squared. On the bottom I have 5x. So number 4, the degree of the numerator is greater than the degree of the denominator. So this is where I need to use that leading term test. So I'm going to write out my ratio. So my ratio is negative 4x squared from the top. And on the bottom I have 5x. And then I'm going to simplify it. Okay. So negative 4/5, that doesn't change. And then x squared over x is x. So what I have here is an odd degree negative leading term. And I have to focus on my end behavior. This is the left end. So I am curious about the left end of an odd negative. So according to my leading term test, this positive infinity is my end behavior. Problem number 5 is the same scenario. The degree of my numerator is 4. The degree of my denominator is 2. So the numerator is bigger. So I need to write out that ratio. So 3x to the 4th over 5x squared. I need to simplify that. So I get 3/5 x squared. Okay. And this is an even degree and it's positive. That's an easy one because I know no matter what, left or right, if it's even and positive, the end behavior is positive infinity. And for the last one here, we once again have a case 3 scenario because we have x to the 4th on top, x on the bottom. So we need to simplify that. We get x cubed. So this is an odd positive leading term. And we want the right end behavior. So odd positive on the right is positive infinity. Okay. And so that's how you find the end behavior of a rational function. I call this the comparison test. So compare the degree of the numerator to the degree of the denominator. And if they're equal, their limit or end behavior is equal to the ratio of their leading terms. The numerator is less than the denominator, then the end behavior is automatically 0. And if the numerator is greater than the denominator, use your leading term test to find your end behavior. And that is how Bakker breaks it down.